Hello and welcome to this tutorial on binary multiplication and how a simple CPU can perform multiplication. In this video I will cover multiplication by repeated addition, multiplication by shifting and adding, as well as hardware multipliers. The prerequisite knowledge required for this video is that you should know what a binary number is, how to add binary numbers, and you should know how an AND gate works. So how do we multiply normally in base 10? So if we take 5 times 3, we know that that equals 15. We could interpret the multiplication as 5 lots of 3, which means that we have 3 added to itself 5 times. And this does give us the correct answer of 15. So then how would this look in binary? So if we have 5 times 3 in binary, then we have 3 added to itself 5 times, which in binary gives us 4 ones, which is the equivalent in binary of 15, which is the correct answer. So what would this look like in code? And here we have some high-level B code, which should be fairly easy to understand. First of all, we set the input variables A and B to equal 5 and 3. Then we set a variable called counter to equal A, and we set a variable called answer, which will contain the answer, equal to 0. Then we start a while loop, and this loop carries on going until whilst counter is more than 0. And in this loop we repeatedly add b to the answer and then we subtract 1 from the counter. This loop will carry on going until we eventually get the correct answer. This program here is written in relatively low-level URCL code. This is the exact same program as the program we looked at just now. We first of all start by setting register 1 to equal 5 and register 2 to equal 3. This is setting A, which is register 1, to equal 5, and B, which is register 2, to equal 3. Then we move register 1 into register 3. This sets the counter, which is register 3, equal to register 1, which is A. Then we set register 4 to 0, which is the answer. Then at the beginning of the while loop, if register 3, which is equal to the counter, if that register is equal to 0, then we branch to the end of the while loop. And inside the while loop, we add register 4 to register 2 and put the result into register 4. So register 4 is the answer and register 2 is B. Then we decrement R3, which is the counter. And finally, we jump to the beginning of the while loop. So what we just did was multiplication by repeated addition. Note that 5 lots of 3 does not necessarily equal to 3 lots of 5. Well, it does from a maths standpoint, but from a program standpoint, they're not necessarily equal. This is because one of these requires more addition steps than the other, and every addition step means one loop of the while statement. So what this means is that one of these is faster than the other. Specifically, 3 lots of 5 is faster than 5 lots of 3. So in general, if we have A lots of B, then that will be faster than B lots of A if A is less than B. Now, how else can we do multiplication? If we have 20 multiplied by 21, we can split the 21 into 2 times 10 to the power of 1 plus 1 times 10 to the power of 0. We can then expand the brackets out, giving us 20 times 2 times 10 to the power of 1 plus 20 times 1 times 10 to the power of 0. And then you can simplify that to 40 times 10 to the power of 1 plus 20 times 10 to the power of 0. And if we add those together, we get 400 plus 20, which gives us 420. So what would this look like in binary? So if we take 5 times 3, we can split the 3 into 1 times 2 to the power of 1 plus 1 times 2 to the power of 0. Then we can expand the brackets to give us 5 times 1 times 2 to the power of 1 plus 5 times 1 times 2 to the power of 0. We can then simplify that to 5 times 2 to the power of 1 plus 5 times 2 to the power of 0, which gives us 10 plus 5, which can be added together to give us 15. Note that this method still required multiplication, as we had 5 times 2 to the power 1 plus 5 times 2 to the power 0. So how could a simple CPU do that? Note that we only have to multiply by powers of 2, and we can multiply any number by 2 by simply adding the number to itself. Adding a number to itself is the exact same thing as left shifting that number. So if we take all of the bits in our number and move them, shift them to the left by 1 bit, we get that number multiplied by 2. What this means is that this method can be performed only using left shifts and adding. Hence, this method is called multiplication by shifting and adding. So what then would this look like in code? So this program here is a B code version of the algorithm we just talked about. So first of all, we start by setting A equal to 5 and B equal to 3. Then we set a variable called shift equal to 1. The variable shift will keep track of the particular bit that we're interested in. And we start with the first bit, which is 2 to the power 0 or 1. Then we set a variable called shifted A equal to A. So this keeps track of the left shifted version of A. Then we set answer to equal 0. For the while loop, we continue doing the while loop provided that the shift variable is less than 16 or 2 to the power of 4. And we start by doing an if statement, and the if statement tests if shift ANDed with B. So what this is doing is it's checking to see if the bit in B is set or not set. If it is set, then we do the if statement. If it's not set, then we skip the if statement. So if that bit is set, then we add shifted A to the answer. And in either case, we then left shift shifted A once, then we left shift once. And that loop will carry on going until we get the correct answer. So this code here is a URCL version of the program we just looked at. First off, we set register 1 equal to 5 and register 2 equal to 3. So that's the A and B variables. Then we set register 3, which is shift, equal to 1. We then move register 1 into register 4, which is sets shifted A equal to A. Then we set register 5 equal to 0, which is the answer. Then at the beginning of the while loop, we test if register 3 is greater than or equal to 16. And if that is true, we skip to the end of the while loop. Then on the inside of the while loop, we have the if statement. So first off, we AND register 3 with register 2, which ANDs B with the shift variable and puts the result into register 6, which is a temporary variable. Then we test if register 6 is equal to 0. If it is, we branch to the end of the if statement. Otherwise, we do the inside of the if statement, which simply adds register 5 to register 4, which is the answer added to shifted A, and put the result into the answer. Then we left shift register 4, which is shifted A. Then we left shift register 3, which is shift. Then we jump to the beginning of the while loop. Brilliant! We now know how to multiply using software. Most complex CPUs, however, will have some form of hardware multiplier. So how could we implement what we've just learnt into hardware? When we were multiplying 5 by 2 to the power of 1 and 5 by 2 to the power of 0, we were essentially multiplying each bit one at a time. So how do we multiply a single bit? Now if we write out a truth table for A and B and A multiplied by B, then we can start with 0, A, and 0 for B. And if we multiply 0 by 0, the result is equal to 0. Then if we multiply 0 by 1, the result is also 0. And if we multiply 1 by 0, the result is also 0. Then, finally, if we multiply 1 by 1, the result is 1. So what you should notice is that this truth table is exactly the same as an AND gate. So we only get a 1 in the result if both A and B are equal to 1. So, for a single bit, A multiplied by B equals A and B. So now we have 5 times 3, and what we need to do is AND each of the bits together. So what we need is a matrix of AND gates. What we can do is represent this as a table by putting A as the columns and B as the rows. Then we can fill in the table, ANDing each of the bits together. Now what we can do is write down all the powers of 2 that A represents and the powers of 2 that B represents, and then we can multiply those together in our table to figure out what each bit within our AND table represents. From the table of ANDs, we have 4 1s. Those 4 1s correspond with these 4 values here. If we take these 4 values, these 4 powers of 2, and add them to each other, then we can write that out in binary since each of these represents a single bit. And if we add that together, we get our result of 15, which is the correct answer. So if we want this to work for all 4-bit values of A and B, we must add all of the values in the table together. If we line up each of the values that we get from our table into distinct rows, then we can line them up like this. Now what we can do is add the left 2 sets of values together, as well as adding the right 2 sets of values together. This gives us the values in the table below. Finally, we can now take those 2 sets of values and add them together to get us 8 powers of 2. These 8 powers of 2 represent the bits within our final full answer. Now if we take what we just discussed and put it together into a diagram, we get this. We first off put the A and B values into our 4-bit AND matrix. We then put that into 2 4-bit adders. We then put that into an 8-bit adder, which then gives us our final answer, which is 8 bits. Note that the number of bits in the answer is equal to the number of bits in A added to the number of bits in B. And with that, that is everything I wanted to cover in this video. If you've made it this far into this video, please consider liking and subscribing. And with that, cheerio!